So I'll just proceed. We are going to go into the software. Let me share my screen. Please type a 1 if you can see my screen. Let me know that it is visible. Let me know if it's visible. Drop a 1 if my screen is visible. Drop a 1 if my screen is visible. Super. So I can see my screen is visible. So I'll just proceed to what we are going to do today. So at this point, we've designed the beams. Now I want us to design columns. All right. And when designing columns, there are a few things you may have to consider. So when it comes to design of columns, we basically have two major types of columns. We have the short columns and the slender columns. It is important for you to consider this as you model your structure. Okay. So if you are doing, say, majorly the high-end mansionettes, which have double volumes, and they have columns that are going to be in lengths of 6 meters, etc., you need to consider that those columns may be slender. All right. And then to get to know if the columns are slender or not, uh, you can do that manually. You can get to check the effective length of the column and to divide it by the radius of gyration just to see if it is slender or not. And by the columns being slender or say slender or stocky, they affect the failure modes majorly. So for the slender columns, they are easier to bend or they are easier to fail through backing. All right, and then for the short columns, they are majorly going to fail through compression or just punching through the midsection or the midsection of the columns. So that's one of the things that you may have to consider when designing your columns. And then the other thing that I would want to bring to your attention is when it comes to designing the walls. So in Revit, not in Revit, in Robot, the walls are majorly treated as panels, and I'm going to show you how we design them. There is something we may have to do so that we can be able to design them, but I'm just going to bring that to your attention once we get there. All right, so let's go to column design. I will go to my 3D view so that we can see the columns only. I will I will turn off the meshing. And then after I turn off the meshing, I will go to the object inspector. I'll go to the object inspector, select my columns, select all of them, and view them in a new window or in a separate window. Then in this separate window, you can basically see your columns. And when you have your columns, I want you to notice this. We have the columns that lie on the outer edge of the structure. And then we have the columns that are say, in the middle of the structure. Okay, so we have columns that are, say, within the mid-center or near the mid-spans of the structure. And then we have the columns on the on the outer side. So when designing columns, you may want to consider this as well. The columns on the outer edge of the structure are more likely to experience more movements as compared to the columns that are within, are near the center of the structure. All right. And then for the columns that are within the center of the structure, they are more likely to experience more axial loads. So you may need to consider that. So when designing your columns, when getting to choose which columns to design, it would be better if you grouped, say, your outer columns together and then your interior columns separately, so that you get columns that are more likely to behave in a similar way structurally. All right, so we have that. So I'd like to view the results for these members so that we can get to see what are the loads we are working with, okay? And then also the moments that we are working with. So I will turn off the section shapes. And then to view the results, to view the loads, I hope you remember how to do this. You go to results and then diagram for members. So to see any results for members, members are basically beams and columns. You go to results and then you go to diagram for members. And then at this point, you can be able to see or to turn on the loads that you want to see or the internal forces that you want to see. So Fx is the axial force. So I will turn on Fx. Then I will go to tabs. go to parameters, and then turn on labels, change it to differentiated and fill. Then I will click on apply. Once I do that, I will be able to see these, say this confused or this, these say disorganized drawing. So then I'll just zoom in and click on normalize. So I'll zoom in and click on normalize again, and then you can see your results. So this is still not very, very clear. I think I will have uh, to, to filter out some columns so that you can be able to visualize this. But what you can get from this is that the software is always going to highlight your most critical case. So the column that has the most load is always going to be highlighted in red, and the column that has the least load is always highlighted in green. So this one is not the best view to see this because we have all the columns here. So I'll just exit. I will just exit, and then I will start with my story one. So I expect most of my actual loads to be at story one. So I'll just go to the object inspector, expand story one, then select the columns here. Then once I select all the columns in story one, I'm going to view them in a new window. So with this, at least I have a few columns. They are going to be a bit easier to visualize. So I'm going to turn on FZ, and then I'll just apply. It is better to go to parameters, ensure the labels are on, and then have the positive and negative moments as differentiated and filled. Then you can now visualize the results. And then these results are just due to 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 the self weight. Remember, the results displayed here are always case sensitive. So for you to see the worst case scenarios, you need to select one of the ULS combinations. So at this point, you're just interested in identifying the worst or the most loaded column. So I'll just go with the ULS combination. And then once you click on apply, you can see the loads have increased significantly. So now you can see that we have loads in the regions of 1900 or almost 2000 kilonewtons. So this is what I was saying. For the columns near the centers of the building, they are going to be experiencing a lot of axial loads. You expect most of your axial loads to be here. And then for the columns on the outer edge, they are not going to be experiencing a lot of axial load. Okay, they may not experience as much axial load as the ones inside, but these ones are more likely to experience more movement. So if I turn off the axial force and then turn on the major movement here, you're going to see that the columns within the interior of the structure, they have uh, they have they have less moments as compared to the ones on the outside. So this one becomes important because when designing columns, you have to consider these two elements together. You're going to be considering the axial loads and the moments together. So I'm going to take you back to something that you may have covered in your undergraduate studies, and that was the uh, interaction diagram, the moment and shear and the axial loads interactive diagram. So it was basically a graph. Okay, so you have a graph. This is the y-axis, and then you have a graph, and this is the x-axis. And then you had some sort of parabola. Let me use. So it might not be very perfect, but I hope you just get the gist. Hey, what's happening here? Let me use a straight line just for ease of drawing. So it was basically more of a parabola than these straight lines. You're going to see how it looks like in the software. You're going to see how it looks like in the software. And these uh, axial load and the moment interactive diagram, this is how it used to work. Along the y-axis, you have your axial loads, and then along the x, these are your moments. So this interactive diagram is basically a failure envelope, if I may say that. It's basically a failure envelope. And what we do when designing columns is we get to choose the acceptable combination for moments and axial capacity for given members. So if we have a given cross section of a column, the uh, the the interaction diagram basically shows us the acceptable combinations for moments and axial loads for this given cross section. All right. So when you have, say, your axial forces in this direction and your moments in this direction, you're going to, you know how to read a graph. So you are going to have a value like along the x, you have your moments. How do I write this? So here, say you have your moment. So if you are to read this, you would have M here and uh, the axial load here, P. So anything that is within these, any combination that is within this failure envelope or this graph here, anything that is within here, it is safe. But if anything appears outside here, it is unsafe. So that's why it is important to basically understand how these movements work, and so that you know you cannot treat them as two separate things. Okay, you cannot treat the axial loads and the moments on a column, sorry, as two separate entities. You have to consider the combined effect of both of them. All right. But the beauty is this, you do not have to do this manually now that you are using the software. The software is going to do that for us. So what you need to do is just understand that those elements are supposed to be treated in a combined way, and they are not, say, mutually exclusive. They work together. All right. So that comes into play because when you are choosing which columns to design, you get to select columns that are likely to experience the same effects both in the axial forces and in the moments. So we said for the outer columns, they're likely to experience less axial loads, but more moments as compared to the internal columns. And then for the interior columns, they're more likely to experience more axial loads and lesser moments when compared to the outer columns. So when you want to design your columns, uh, you can choose to decide to design for all of them. You can choose that. You have the power to do that. But the thing is, it becomes a bit tedious to do that and also unnecessary. Okay, so what you do is you always try to group them. You get to see which columns have loads that are within the same range. You get to decide on a range. You get to see if it's the interior columns, I want to group, say, any column with, say, a load higher than 1500 kilonewtons. I'm going to design them with this particular load. So you go with the critical, with the worst case column, so that if that column is supported by can carry that load, then the other columns that are carrying a lesser load, they are also going to be safe. So all these things, everything that I've just been saying is just to give you a background on on how to select the columns to design. All right. So I will turn on the axial load here, the FX, and then click on apply. Then I will zoom in and normalize so that you can get to see the loads. So this is what I'm saying. So when you want to design the columns, you can choose to design for all of them. But the thing is, if you get a section and rebar that works for this column here with a 1986.59 kilonewtons, then that section is going to be safe to carry this load. It's going to be safe to carry this load. All right. So you can get to choose this column to design for that. All right. Then the other thing is, I would not recommend you go with this section to design for this column here because this column is carrying a load of 1900 kilonewtons. This one is carrying a load of 325 kilonewtons. I hope you can see how significantly large this is, right? I hope you can see how significantly large this is. So by doing that, you can see that if you design for this column, if you design for this column with using this load, it becomes, you're going to over design for this particular column here. Okay, you're going to over design for it, and your design is going to be basically too expensive for no reason. And it's not that it would be, say, it would be too much work to design for this column. So what we typically do is we decide which columns to design. So we can say that for the columns that have, say, 1500 kilonewtons and above, we are going to design them using these columns. And then say the columns on this outer edge, we are going to go with the, I'm sure you are muted. And then for the columns on this outer edge, we are going to select the worst case scenario on this other end. Same case to this face, same case to this other face, and this other face here. All right, so that you can end up with probably just a maximum of 5 to 6 columns whenever possible. All right, so let's do that. Let's begin our design. Let's start our design. So to design columns, it's really easy. It is really easy. All you need to do is select the column you want to design. Okay, so just select one column. And then after you select one column, you go to design. And then when you go to design, you go to provided reinforcement of RC elements. So when you do this, you're going to be taken to the design layout. Okay, once you do this, you're going to be taken to the design layout. So just going to take a minute to load and take us there. But once we get there, we are going to proceed. So let me give it a moment. Okay. So let me click on OK. Okay, and then we are good to go. So we are here at this time. So this is the design. This is the design layout. Okay, and you've been here before, especially when designing the beams. So at this point for the columns, we are going to notice that we are not assigning supports. So we just click on OK. You go with manual combinations, and then you click on OK. Then once you are here, now you need to just design your column. We selected them from story one. So you can see when you expand story one, you have the column here. Then something that I recommended you do when designing your beams is that you name these members as you go. So for example, we can say that this is going to be our column one. So call it, say column column one. Let me show how let me repeat on how to rename them. You just right click on the column, and then you go to edit, and then you click on rename. Then you type the name. Say, let me call this column one, and I think its cross section is 350 mm by 350 mm, and then you have to press enter. You have that. So you have it. You have it. You have it you have it you have it named. So it becomes easy to remember. Then once you have it named, now you have to set the three elements we set earlier. We set the story parameters, we set the calculation options, and we set the reinforcement pattern. So to set these things, it's really easy. For the story parameters, we don't need to set anything. So we can just save this as it is. In the environment class, we have XC1, and in the structure class, we have S1. So I'll just save it. I will just save it as XC1 and then click on OK. All right. Then I will go to calculation options. This is, say, the most important bit. But for the columns, it's much easier than what you had with the beams. So under general, we literally do not have to make any changes. But if you want to set the cover or increase the cover to something like 35, you can do it from here. Okay, then you have concrete. So for the concrete, always ensure you're using the material that you're going to have on site. So if you're using a higher class, go with it. But for most structures, you're going to find that you're using class 2530. And then remember, the higher the class of concrete you select, the stronger that concrete will be. So it means you're going to end up with smaller sections and lesser rebar. So it's always important to note that so that you do not go with a class stronger than what you are going to use on site. It's actually even better if you designed with a lower class and then you cast with a stronger class. Okay? Because uh, essentially you are going to be safe. But if you did it the other way around, you design with a stronger class, then cast or build with a lower class, your structure is going to be, or your design is going to be unsafe. So I'm going to go with class 2530. Then I'm going to set the longitudinal reinforcements. I prefer to work with class C. Then I will uncheck the bars. For columns, we recommend a minimum diameter of 16 millimeters. So I'll work with 16 millimeters diameter. Then I'll tick 20, 25, and 32. Then I'll go to transverse reinforcement. For the links, I'll select 500C again. And then for the stirrups, I will just turn on 8 millimeters. And then I will choose to save as. So these are calculation options. I will call them columns calculation options. Then I will click on OK and OK. Then I will go to the reinforcement pattern. So you're going to notice some of these things are really easy. So for the reinforcement pattern, we actually don't need to make any changes here. All we need to ensure that the transverse bars, the stirrup is 135 degrees. So once you ensure this, uh, you can save it as a columns reinforcement pattern. So for the columns, you don't have to do a lot. There isn't a lot to do. So you just click on OK. Then once you do this, once you have them set, once you have them set, once you have them set, you just click on calculate and the software is going to calculate and design for you. So you can see whenever the green tick is checked, whenever this tick is checked, it means it has been designed and it has passed the design checks. If it is yellow, it means it has been designed, but it fails on some instance. Okay, and then when it's not checked, it means that the design is yet to be done. So I'll go to column results, and this is what you have. So what you are seeing here is what we were talking about earlier on for those who have joined us. So what you're looking at here is the interaction diagram. But since our robot is more advanced than what you are doing, it is using a 3D interaction diagram. All right. It is biaxial because you have bending along the two axes. You have the MZ and the MY. So if you remember from our very first class, we had this section here, and then we said we have moments in this direction, and we also have an axis in this direction. So when it is biaxially, when we say when we say we have biaxial bending, uh, we have bending in both directions. So uh, along both axes, right? And then this is where you get the interactive interaction diagram, and this is what you are saying. Along the y, you have along the y you have the axial load, and then along the x you have the moments, right? So something to note is that anything above the x-axis, anything above 0, this region where I'm hovering with my cursor, it's compression, and then anything below the x-axis, it is going to be the tension. All right. And then the point where these failure envelope crosses the x-axis, this point is known as the point of, say, pure bending. At this point, the column is just under pure bending. So what you are going to be looking at when looking at this interaction diagram is just ensure that both of these ticks are within this plane. Okay, both of them are within this plane. If they just go outside, your column is failing. Remember what this shows us that the axial loads and the moments work together. So what you are looking for is a combination or an we are looking for an acceptable, okay, a combination that is acceptable for the cross section that we chose. Okay, so you have your column results there. This is just in 2D, the interaction diagram in 2D, and then here you have the interaction diagram in 3D. And then you can see the main movements are always along Y if you had chosen the direction correctly. Then we have the column reinforcement. We have the column reinforcement here. So you can see the column reinforcement, you have 20, you have 6 T20 bars, and then you have stirrups at 200 mm. So those are your bars. Then you have the calculation notes or the column calculation note, and you can just go through it. You can see all the items that have been calculated. So for the elements you were talking about earlier, the slenderness ratios, you can see that for this one, it's actually a slender column. Okay, okay, you have that there. Then you have your backlink analysis. You have your reinforcement, and then our ratio is 1.54%, below the 4% that is maximum. So basically, that is what you have. That is what you have, and that's how you design columns. So it's really easy to design columns. So I'll go back to geometry, and then I will show you a way to design, say, more columns. So I want us to design a few more columns. So I will select the columns at story one again, and then I will click on edit in new window. So this time, I want us to design columns along this edge. So this method I'm going to show you is we are going to select multiple columns, and then the software is going to design for the worst case scenario. So you can use this method most of the time. This is actually the method that you're going to be using most of the time. So when you want to design, say, for columns along this edge, and you just want to design for the worst case scenario, you don't want to go through the hassle of having to select the worst case scenario manually by turning on the results and then viewing the actual loads and moments. You can let the software do that for you. All you need to do is select the columns that you have combined. See, we saw these columns, these outer columns, they are within the same range in terms of actual loads and moments. So you just select them, okay? You just group them, you decide or just check which columns are within, say, a similar range. And then after you've selected all that group of columns, you go to design, and then you select provided reinforcement of RC members. The same workflow, provided reinforcement of RC elements. And then the software is going to transfer them here. Ensure you're working with manual combinations, and then you click on OK. All right. Then once you do that, I just, I think I did that wrong. Let me repeat that. Let me just select them, then go to design, provided reinforcement of RC elements, click on OK. Okay, so you have that. So when you have this column selected, you can see they have been, say, named. Uh, Let me rename this. You can see they have been renamed, say, column 14 to 34, column 10 to a given number. So what you do is you design for one of them. Okay, you just design for one of them. You can design for multiple, but you can design for this range only. So you just select the one with the range, and then you click on reinforcement. So select the columns reinforcement pattern, then the column calculation options for the columns, and then the story parameters. And then once you do that, you just click on calculate. Remember, we had set these ones earlier, and then you can just go through the results. You can see the interactive diagram. You can see for this one, it's not as large as the other one was. Okay, and then something you may need to note about this interactive diagram. The side on compression is way larger than the side on tension because concrete is not a good tensile material. So that's why this lower side is usually like very small. You can see the distance from 0 to this point is much smaller than this upper part. Then you can go to reinforcement. So you can look at the reinforcement. You can see the main bars for this one. They have smaller diameters than the others, than this particular, than this particular than this particular column that was, say, having the highest load. This one requires 60-20 bars, while this one requires just for the 16 bars. You can see the main bars here. So to make your work easier, this is how you design for them all together. You just select one, press Control, and you select the others. Then in these parameters here, because we had set them earlier, you just click on the drop down and you select column reinforcement parameters. Okay. So you select the reinforcement patterns that you had created, the calculation options, and the story parameters. Then once you do this, just click on calculate, and then they are going to be designed. So you can quickly go through the results. You can quickly go through the results, get to identify the column with the most reinforcement. They have the same section. So you can just select the column with the most reinforcement. So you can see that this one had 40-16 bars. This one also has 40-16 bars. This one has 40-16 bars, and this one has 40-16 bars. You can see they are almost within the very same range. If you want to look at their axial loads, you just go to column results here. And then here is where you have the loads that have been used in design. So you can see the worst case scenario here. It's the ULS with wind in the X plus direction. And this one makes sense because it's along the direction, along the plane which we use to simulate the wind. So you can see that one is the one that was used as the most critical load. You can see for this one, the axial load was 246.53 kilonewtons. Then for this one else, it was 363.86. Then we have 294. We have this one has 755. Okay, this one is on the higher end. Then we have 129, and then this one has 2000. So we'll go to the outer ones. Now this column 10 to 11, you can see it has the highest loads. So you can just use its reinforcement to reinforce for the others. But it's always nice to check the others so that you ensure they are just within the same reinforcement. You can see all of them require the same amount of bars or rebar, and they also have the same cross section. So when it comes to detailing and when it comes to generating the report, you could give them the same report. Okay, you could assign them as one column. So I'll just select this one that we have decided on it being the critical one, and then rename it. So I'll just right click, go to edit, and rename this. Then I will call this column, say column 2 to 200 by 500 mm. Then press enter. Then when I come to generate my results or my calculation notes, I'll just select this one and then go to calculation notes and generate the report. Okay, so instead of you having a calculation note for all of them, you are drawing, or your design reports becomes too large. and there is no need for that. So you can just use these two to design them. So I'll go back to geometry. I want us to design as many columns as we can together so that it will be a bit easier for you to do on your own. So I'll still work in story one. I'll select all my columns and go to edit in new window. I'll just maximize this and then I will press escape. Let me turn on my section shapes. And then this time I want to design for this column here. So this column here has a span, this column here has a section of 350 by 350, but we have this interior column here that has a section of 200 by 500 millimeters, right? So we can do this. You see all these columns, all these interior columns with this section, 200 by 500 millimeters. We can select them. So just select one, press Control, and select the others. Okay, since these are interior columns and they have the same section, we can design them and see if they pass the design and also which one is the worst case scenario. So the one that we have the worst case scenario as is the one that you're going to use to reinforce the other columns, all right, that have the same cross section. So with these columns selected, I will go to design and provided reinforcement of RC elements. It is going to take me back to this point here. So I'll just click on OK. For the columns, it's that easy. And then you have this there. So this time they have been changed together. Last time did not allow me to do that. But this one is even better because if they're changed together, the software will just design for the worst case scenario for you and make your work a bit easier. So select the reinforcement pattern that we created, then the calculation options that you created, and the story parameters that you created. And then after you do that, just click on calculate and get to see what happens. So it passes the design. So you can go to calculation results to see what you're working with. So you can see the worst case scenario is the ULS with winds in the X positive direction. And this is the beauty of using the software. It is able to it is able to it is able to select the worst case scenario for you. And then something that you may find interesting here is that we have combinations that have more, that have a higher, that have a higher, say that have a higher axial load. So the N is the axial load, and then we have the MY, this is the moment along the major axis, and MZ, the moments along the weaker axis. So if you look at the ULS with X positive, you can see that this large moment here has been considered to be the worst case scenario. Okay, the one that was selected initially is the one that was considered. The one that is always blacked out is the one that was considered to be the worst case scenario. So it's the one that is used in design. So you can see the moments play a very big part. So it's more of a combination. These two elements are not to be treated exclusively. They are to be treated as say elements or elements with the same effect or an effect, or they act together. Both of them have an effect on the design. And then basically what the software is looking at is looking for a combination that is acceptable within the failure envelope. So this red line is the failure envelope. Okay, so any combination that is out here, say if you had a moment that was say 60 and then an axial load that was 2000, it would be outside the failure envelope. So this design would have failed. Then you can look at your reinforcement, get to see what has been calculated. You can see for these ones you only require main reinforcement of 60-20 bars. All right. So when you go to do your detailing, this is the beauty of this. So instead of you detailing all columns separately, I want you to imagine this scenario. You are detailing this column. It has a different reinforcement to this one, and this one. So there you have 4 column sections. Then here you have 4. You're going to end up detailing like 25 columns. It's going to be a lot of work. Even on site, it's going to be a lot of work and it's going to bring about confusion. So whenever you're designing, you want to make it relatively easy for everyone. For you yourself, as you're going to be doing the detailing work together, for your approval purposes as well, and also for the guys on site. So that's why we always group the columns together. So you can see that these columns here, they have the same cross section and they are within, say, almost the same region in the structure. So you expect them to have, say, similar loads or similar design. All right. So we're going to do the same thing on this outer edge. Okay. So these columns here are on this outer edge. I'm not going to select these two because they have been oriented differently to this one. So I'll only select this one, and this one, because they have been oriented in the same direction. Then after I select them, I will go to design and provided reinforcement of RC elements. Then once you do this, just click on OK and close. So I should probably rename the one we just uh, designed. So this was column 3, say 200 by 500 mm. Okay, let me rename it again. You have to press enter. Then I will call this column 4 so that it's easy for us to remember which columns those were. So 500, press enter. And then once I have this string, I will just select the reinforcement patterns that we created and the story parameters. And then you just calculate. Then once you calculate, you have your interactive diagram right here. You have your column reinforcement details. You can see for these ones, you only need 4016 bars. Okay, so that's how you can work with this. Okay, so that's how easy it is to design columns in robot. That's how easy it is to design columns in robot. So I want to show you something else that you should consider doing. So when you're designing columns, you expect that the axial loads to reduce as you go upwards. All right. So if you are to select all columns, sorry. Yeah, if you select all columns, just as we have done here, we expect that the axial loads are going to be increasing going downwards. That is, we expect these columns at the bottommost story to have more axial load than the ones at the top. So what you do, this is for economic purposes. You don't have to do this, but for economic purposes, you may choose or you may decide to design other columns at a given level. Okay, say we designed the columns at story 1, then you may decide that for the same columns, say you can design for them at story 3, and then use these details for all the columns above story 3 all the way to the top. Okay, you're going to notice that at this point, probably the amount of rebar required in some instances, it reduces. Okay, so this is going to be pretty common for you, especially when you're working with taller structures. Do not expect the columns at the ground floor to have the same amount of rebar with the columns, say, at the 7th story or the 8th story. So to cater for that and also to be economical so that you do not hurt your client so much, it's always just good practice to design for the same string of columns, but at a different level. So I hope you can remember some of the columns to design for. I'll just go to story 3. I will select all columns at story 3, and then I will view them in a new window. All right. Then I will start with the columns that we just designed, or I can start with these ones, the 350 millimeter columns. So we have this one, we have this one, and we have this one. Okay, so you can see these columns that we designed as our column ones, the 350 by 350 millimeters columns. So just select them, say in story 3 or story 4, then go to design and provided reinforcement for RC elements. Then once you do this, click on OK when this appears. Then go to where is my okay? So these are the columns here. These are the columns here. Story 3. So I'll select them. Then I will select the column reinforcement pattern we selected, the calculation options we created, and the story parameters we created. Then you click on calculate. Then once you click on calculate, I want you to compare the results. So these are the same column. So this is just column 1. I can edit here and rename it. Say I can call this column 1 as well, and press enter. So you can tell this is column 1 and this is column 1 as well. But now I want you to view the difference in the results. So if I select column 1, the one at story 3, and go to column results, let me see. Okay, let me see where that. Okay, I'll just compare the results in the column notes. I'll just compare the results in the column note. So I'll just compare a few here. I want you to look at the ULS, or the forces used to design. So the force used to design here is 1066.49 kilonewtons. And then if you select this one, the force used to design is 2018. So you can see there's a difference in almost 500 kilonewtons. I don't know where my table went to. Sorry, I don't know. I do not know where my table went to. So that's the reason I'm using my column note to see the forces used in design. So you can see the results that were used here in design. So the internal force at this point was 20 or 2000 kilonewtons. And then for the same column at story 3, the result used was 1000 kilonewtons. You can see it's a difference of almost or just slightly over 1000 kilonewtons. So that's going to have an effect on the design. That's going to have an effect on the design. So at this point, you can see at story 3, going upwards, we only need 4016 bars. But if you go to the column at story 1, you need you need 620 bars. So you can use this. You can use this to detail to you can use this just to detail your bars and make them a bit more efficient. Okay, so uh, that's with regards to designing columns. That is with regards to designing columns. It's, I think, pretty easy. I think it's even easier from the beams and probably the slabs. So I'll just go back to my structure, press escape, and we have our structure right here. So at this point, I'd like us to design the shear walls. Okay, I'd want us to design the shear walls, and you're going to do this in two ways. we are going to do this using the we are going to do this using the required reinforcement, the theoretical way, and then we are going to do this in the provided reinforcement method. So I want to show you something that you may interact with or is going to happen a lot, and how to get over it. Okay, so let's get started. So when it comes to designing the the walls, it's really easy. So the first thing that you have to do is just go to your geometry, go to your member selection. All right. Select panels. So to select panels, all you need to do is go to member selection here. Then in this selection dialog box, you click on this drop down to change to panels. Then select the lift core wall and use these two arrows to select them. Okay, you select them, then you use these two arrows to select them. Then once you have those numbers, just highlight them and copy them. Okay, you just highlight them and copy them. And you can also go a step further and view them in a separate window so that it becomes easier to design for them. My friend here did not create openings in these two floors, but no worries. You're going to use it as it is. Okay, so we have that. So we are going to go to design this. We're going to start with the theoretical method, a similar thing we did with the with the slabs. So to do that, we said you go to design, and then for the slabs, you go to required reinforcement of slab stroke walls options. So you have this option here. And at this point, I need us to select or create the code parameters. Okay, so just click on this option, then you go to code parameters. Then once you are here, we need to create a code parameter for our walls. So click on this page icon to create it. I'll repeat that. So to create the code parameter to be used for design, you go to design, then you go to required reinforcement of slab stroke walls because you are designing walls. Then you go to code parameters over here, and then you click on this page icon to uh, to to create it. So we can call this wall design. Okay, we can call this wall design. And then in the type of calculation for shells, remember what we said in the slab design class. We said for walls, because they are under bending plus compression and tension, we are going to select bending plus compression stroke tension. But if you are working with slabs, you go with simple bending. But for walls, you go with bending plus compression stroke tension. Remember, they are always going to work in a similar way to columns. They are your vertical members at this particular point. Okay, so select the bending plus compression stroke tension. Then you go to materials. As I recommended last time, please uncheck this and select the material manually. So you uncheck as in structural model, ensure this is not checked, and select the appropriate material. So at this point, I'm going to select class 2530. I'm going to select class 2530. That is what we are using. And then in the cement class, normal is the most common one. But if you're using rapid or slow setting cement, you can use this. Then we have the structural class. S1 is usually sufficient. And then the characteristic strength, I'm using 500 MPa. If you are using a different value to change this, all you need to do is left click twice and type the value manually here. Then press OK. Then I'm going to go to SLS parameters. I'm just going to change the environment class to XC1. And then, XC1, then go to reinforcement. I'm going to leave them as B12 bars, and then I will click on add. I'll just click on yes, and then close. Then after I have my wall design code parameter here, I will paste the numbers that we had earlier. So I'll paste the numbers we had copied and then click on apply. And they are going to be applied. Then after you do that, you go to design. and you go to required reinforcement of RC slab stroke walls. So this is basically step 2. So once you are here, remember what we did the other time. So we deleted all list of panels. We deleted this number here. Okay, I hope you can see this tile box. So we have a slab and shell. So the list of panels to be designed has been listed here. So to select the ones to be designed, you can click on these 3 dots. Then remove everything. I'll just delete. Then select the lift core wall, and you design them. So you select them and you use the 2 arrows to select them. Then you click on close. Then to select the limit states, you start with the ULS. You click on these 3 dots. You go to combination. You select you select all the ULS combinations here and you add them. Then you close. You're going to see that they become listed. Then in the SLS, you do the same thing. You go to combination, you select the SLS combination, you add it, then you close. Then after you do this, all you need to do is calculate. So let's give it a moment to calculate. Yes, so once you stop seeing the green icons that were here, it means your design has been done. So you can just click on close here and just extend this. Then I will paste the numbers here, or I can select them. So let me select them. To select them, just click on these member selection here. Change this to panel, then select your lift core walls. Then once they are selected, click on view in new window. Then once you view them, once you have them in this view window, you can be able to visualize their results. So similar thing we did last time. So we're just going to start with the reinforcement areas. So just turn on reinforcement areas and then you click on apply. So you can see your reinforcement areas. So they're usually quite small. They're usually quite small. You can see not all of them have them, and this is why we do not recommend using. This one may be a bit confusing because it's theoretical. Not that it's not recommended; it's just theoretical. So you can see the areas of reinforcement. Remember, this is in millimeters squared per meter. Okay, so check the spacing. You can be able to see. So you can see you majorly have T12 bars at a spacing of 250 millimeters. It does not make sense to space them at say 10,000 millimeters for this point. So you always go with the smallest spacing that you have. So if you have 250 millimeters as your smallest spacing, you are going to have that spacing right there. Okay, so that's how you design. That's how uh, you design for these members in this manner here. All right. So this is method 1. Now we are going to go to method 2. We are going to go to method 2. It's easy. It's also easy, only that there is say a small caveat to it. Okay. So the first thing you have to do. This is the most recommended way this is the way that I'd recommend you to design these members. So the first thing that I need you to do is go to member selection over here. And then in this selection, select panels. Okay. And then once you select panels, select your lift core walls. Then once you select your lift core walls, I want you to copy this number here. All right. Then once you select these numbers here, I want you to go to Cowalls. And then in the panel selection, just paste them here. Let's tell the software we want these walls to be treated as core walls. That is, they're going to be resisting the lateral loads. So list the numbers here, and then you add. It is going to make changes to it is going to make changes to your results. If your results were previously available, they are going to be turned into, say, unavailable, but that is okay. So just click on yes. This is a step that we forgot to do earlier on, and I just realized. So before you design your walls, just ensure you do this. Before you design your walls, always ensure you do this. Select your lift core walls, and this applies to the lift core walls only. You select them, you go to core walls, and then you paste this number here, the numbers that you have copied here, you paste them here. So this one tells the software that these walls are to be treated as lift core walls. That is, they restrain the structure in the lateral direction, and they also carry the vertical loads. Then once you paste them here, you click on add. So I'm just going to click on yes, and then I will close. Okay. Then I think I'll just rerun the calculation quickly. And then see what we have. So now we wait, let it run. Yes, so let it run. It's going to take a bit of time, but nevertheless, we need to do this. So we'll just wait, and then once we have the results that we need, we are going to proceed from there. So just taking a bit of time, and we'll also have to redo this later on, but no worries. We just wait, and we should not be very far off, not take a lot more of our time, but taking a bit of time. I think it's 4 minutes already, but we have no choice, unfortunately. Okay, so we are done. We can now do our design. So I wanted you to see that you have to turn these into core walls first, and to change them to core walls, it's really easy. All you have to do is go to your member selection right here. Then in the members, select panels, and then select your lift core walls. Then once you select them, copy these numbers. Then once you copy them, you go to the lift core icon over here, core walls icon over here, in this modeling bar on your right. Then you paste the number here and add it. You should see the panels listed here as core walls. All right. So once you do that, you're good to go. The next thing that I want us to do is to design the walls themselves. So we can start with the ones at the bottom. I will just select two. So that let me select the four of them as they are, so that you can see what happens when you try to design them using the provided reinforcement. So when you try to design these walls using the provided reinforcement of RC elements, this is what usually happens. You are going to get this error. Option has not been implemented yet. So if you say Google this error and you go to the Autodesk website, they tell you to change the code. So it's just a code issue. So we need to change the code to a code that this particular design has been implemented in the software. Okay. So we are going to change the code, and by changing the code, it is also going to invalidate our results, and we will have to run the analysis again. All right. So let's do that. So to do that, we are just going to I'm going to go back to geometry. All right. Then once I go to geometry here, it's going to take a bit of time. Once I go to geometry here, or let me do this. Let's go to design, provided reinforcement of RC elements. And then I'll just click on close here. Then I'll go to tools, job preferences, then design codes. The design code we want to select, you'll have to click on these three dots here. Okay. And then you're going to select this one, NFEN. Okay. So you're going to select, at this point, you are using BSEN. So you're going to select NFEN. And then it's a version of Eurocode, but I think it's a national annex, probably in France. So you select the NF Eurocode EN, then you click on OK. Then once you select that particular code, you click on this drop down here, then you click on More. All right. So just to repeat, you click on these three dots. Then you go to NFEN and you select. Okay, so you click on it, then you select OK. Then once you do that, you click on this drop down, you select More, and you scroll down to where you are going to get the version NFEN here. Okay, so you scroll down and select NFEN here. Then once you select this NFEN, you add it to this side using this arrow here. So you select it, then you add it to this box over here. Then once you add it here, you select it, ensure it is highlighted as mine is, then set it as current. Okay, set it as current, then you click on OK. Then click on OK. You're told that it's going to make changes to the database, so just click on yes. That's what we want. And then now go back to geometry. Okay, you can do all that here in the geometry. You can actually do this in one go just to save your time so that you don't end up with the same so that you don't have to redo this twice. So what I would want you to do, is go to member selection, select your panels, and then select your lift core walls. And then after you select your lift core walls, highlight everything here, copy it, go to member selection. You only need to do this once. So you have these as core wall one, and then you paste them here. And then once you paste them, you add them. But since I had already added them, I'll just close. Then once you do that, you go to tools. Then you go to job preferences. And then in the RC structures, you click on these three dots. You select NFEN. Then you click on OK. So you just click on it. And then once this arrow appears to the left of it, you click on OK. Then once you do that, you click on this drop down. You go to More. You scroll down. By default, this one, by default, the NFEN will not be in this list here. So you just need to scroll here slowly, select NFEN, and then you click on this arrow to bring it here. Then once you do that, select it and set it as current. Okay, so once you select it, select this Eurocode. It's just a version of Eurocode that has this parameter enabled. So you select it and set it as current. Then you click on close. Not close, then you click on OK. Then once you have this, just click on OK. Then your results are going to be invalidated. So let me just see. Tools, let me see if that's applied. Okay, it applied. So your results are going to be invalidated. I need you to calculate them, but for the sake of time, I'll just proceed to design mine as TR. I'll just proceed to design mine as TR. But for you, I especially just for practice, just remember to rerun the analysis. Okay. So how is this? I'm losing my cursor. So select them, then select the panels you want to be designed, or I could select all of them just to save on time. I will select all the panels, all the lift core, panels, select them, then go to design, provided reinforcement of RC elements. This time, the software will go through. You can see the other time we were not being able to, we were not in a position to design them. So at this point, we can now design them. Okay, we can now design them. And it is really easy to do this. So a similar thing you did for the columns. So you set the environment class as XC1 and then the structure class as S1. Then you can save them as XC1 and then click on OK. Then in the calculation options, so in general, you have the walls. These are internal walls, so you just leave it as they are. Then in the concrete, you work with plus 2530. In the longitudinal reinforcement, work with B500C. Then I'm going to use 12, T16, and T20. It won't go to T16. It usually ranges within T12 most of the time. Then in the transverse reinforcement, I'm going to go with 500C as well. And I will go with 12, 16, probably 10 as well, but I'd like to work with 12. Then for the wire fabrics, I do not need them. So I will click on Save As and have these as my walls calculation options. Then click on OK and OK here. Then after that, you go to reinforcement pattern, just as you did before. Ensure the reinforcement type is bars. Okay, ensure the reinforcement type is bars. Then the distribution reinforcement anchors, have them in this manner. You can't make any change here, so I think we're just okay. Wire fabrics, we don't need any wire fabrics, so there isn't any change to make here. So I'll just click on OK. Then once you do this, just calculate. And the result is going to apply here. You're going to see it has been checked. So once it has been checked, you can go to reinforcement, the wall pattern, the wall results. So to see the wall results, you have to check all load. You have to check all of them. There's no diagram because nothing had been checked earlier on. So you check all of them and then you click on apply. And then from there, you can see the diagrams. So you can see the reinforcement diagrams, and then you can also see the stresses. Okay, then you go to wall reinforcement. You can see that we have T12 bars. All right, then you can go to your wall notes to have your report. You can see all the reports, and that's how you design shear walls in robot. Okay, so that's basically it. That's how easy it is to do, and you can do this for all levels. So you could start with story 1. If there's a wall at story 1, I'd recommend you can design for one there. The only thing we need to set here is the reinforcement pattern. Then you click on calculate. Then you can see the reinforcement and the report. Okay, so that's how you design for them. And then to export these reports, it's really easy. All you need to do is go to the wall note. And then once you do this, you go to results, a calculation note, have everything as it is, and click on OK. Then visualize if everything is there. If the diagrams are not there, it's always nice to have the diagrams. If the diagrams are not there, just go to wall results, check everything here, and click on apply. Then once you do that, now this time, if you try to produce the calculation note, the diagrams should be there. Then once you have this, save as, I want to save mine in the design reports, and then you can have these as the lift core design reports. Then save it. So design as many of them as you can. It's literally it's quite easy once you set the right the right code. Okay, so that's how you do that. I will also design a basement wall. I will also design one of the basement walls because it's the same procedure. It is the same procedure. So uh, we are going to design for one of them so that you can just view it. So let me turn off the let me turn off the what the mesh, then select one of them. Basically, they are going to be acting, they're going to be having the same load because the basement walls are not meant to carry the loads from the upper floors. They are basically here to prevent the soil from going into our basement. And we have the same soil parameters all around the structure. So you can just select the largest one. And then once you select the one that looks the largest, you just go to design and then provided reinforcement of RC elements. Then once you do this, just click on OK. And now select it from here. Once selected from here, you go to, you select the calculation options that you had set earlier, the wall calculation options, then you click on calculate. Then once you click on calculate, you can go through the results, turn on the reinforcement, the diagrams, so that you can visualize the diagrams. Okay, then the wall reinforcements, you can see the wall reinforcement as they are, and then the design report. Okay, and then once you have everything that you need, just go to results, calculation note, click on OK. Once you have the diagrams, once you ensure the diagrams are there, click on File, then uh, save as in the same folder that you had all your reports. Remember, we are going to be combining these reports in the last class so that you can have one design report. So let's call these basement wall design, and then click on save. And then with that, you have your floors or your basement walls designed. All right. So that's how you design your walls and columns in Robot. And it's, I think, literally that easy. I think the most challenging one was usually the slabs, not the slabs, the beams, but it's also not that difficult once you set the parameters correctly. And then the beauty of setting these parameters is that you do not need to keep on setting them for every project. If you're looking at my screen, you're going to see I have so many of them because I have worked on a couple of projects. But so once you set one correctly, you may not have to ever set them again. All you need to do is select them and then run the design. All right. So that's how you do it. For today, we can end the session at that particular point, and then I will see you on Thursday. On Thursday, we'll start working on the foundations. So we are going to start with the part foundations, the combined foundations, and then if time allows, we are going to do the strip foundations. And then next week, we are going to finish off with the mat foundation as we had promised. Okay, so for the roofing, we do not model the timber trusses here. We just decompose the loads for ease of design, and then we use Excel sheets to design the roofs. But I'm sure we can do a truss or two to show you how you can design trusses either timber trusses or steel trusses using robot. We can do that next week as well. Super. So thank you once again and see you in the next class.